Linear Algebra in Actuarial Science by Alan Collins
and Kimberly Vargas.
You might be wondering what could possibly be an actuarial science that deals with linear algebra, but there's actually a couple things, but we're going to talk about Markov chains. Now, for a Markov matrix to be stochastic, all the columns have to add up to 1. If this is not the case, the matrix can be normalized by dividing the components by their summation. Markov property. Present values used to predict the future. Why does this work? It works because all of the past information is stored within that present value. Now, the connection to actuarial science is actuaries use Markov chains to find the behavior of an outcome over a certain amount of time. Here's an example. Here's a question. Suppose that a company controls 44% of the cholesterol-lowering drug market, given the following information. Those that use brand A will stay with brand A with an 82% probability. Those not using brand A, brand B, will switch to brand A with a 25% probability. Find the probability that someone uses brand A or brand B after 3 years.
The first section of this question can be used to create the initial state distribution matrix. As you can see, it says that a company controls 44% of the cholesterol-lowering drug market, as seen in the first row. That suggests that 56% of the cholesterol-lowering drug market is controlled by another company. The rest of the information given in the problem can be used to create a transition probability or Markov matrix. The columns for this matrix represents the current state, while the rows represent the next state, so from and to. Together with the initial state distribution matrix and the transition probability matrix, you can use the information to create a transition diagram. This is what a Markov chain looks like visually. The transition probability matrix is Q sub 0. So to find the next Q, you would use the equation AX equals B, where A is Q sub 0 and X is the initial state distribution matrix. When you multiply that out, you find the probability someone uses brand A after 1 year and the probability someone uses brand B after 1 year. Now, to answer the question from the previous problem, finding the probability someone uses brand A or brand B after 3 years, you would have to make Q1 the next X value, while keeping A Q sub 0. This is done 2 times to get Q sub 3, or the probability after 3 years. So this comes out to 56% of those using brand A after 3 years, while 44% uses brand B after 3 years. Now, what is the long-term distribution under these assumptions? You can find this by finding the steady state vector. As we have learned in linear algebra, to find an eigenvector, you use a similar equation to this. So this is the equation to find the steady state vector. A minus the identity times x equals 0. A being Q sub 0 and I being the identity. So you would need to augment and row reduce to find the x components, which comes out to being 1.38 and 1. However, because the column does not add up to 1, you would have to normalize the components, which is done by dividing the component by the summation of all components. So in the end, 58% of the people stay with brand A, while 42% stay with brand B. In the long run, under these assumptions, the outcome will behave in a way where 58% uses brand A and 42% uses brand B.